Okay, in the previous video, we discussed the fact that a lot of materials are crystalline. In fact, that is certainly true. Here's a piece of quartz. It's crystalline silica made of silicon and oxygen. You can see it certainly looks crystalline. It doesn't have to be transparent. We'll cover that later. But it's got these faces, these facets on it, and that's actually representative of the arrangement of the individual atoms in that. Here's a piece of pyrite. It looks like a beautiful little cube, and that's again representative of the way that the atoms are arranged at the atomic level. Here's a beautiful little piece of bismuth. Okay, I'll show you that here. I'm not sure how well that'll show up on the camera, but it has certainly a very interesting, kind of curious arrangement to it, and that is a function of the way the atoms are arranged at the atomic scale. If you poured some salt on the table, if you looked at an individual piece, you'd see it was cubic, and that's because the atoms are arranged with some cubic symmetry. Before we get into all that, I don't want you to think that everything is crystalline. So many materials are crystalline. Okay, many metals. So for example, in fact, I would say most of the metals that we deal with as engineers are crystalline, highly organized. There's some important ones that are not. There's some glassy metals, bulk metallic glasses and stuff as well, but most metals that we use are crystalline, they're polycrystalline. Some ceramics, I'll say some ceramics. So for example, alumina, Al2O3, which is also called sapphire, is crystalline, and if you've got a recent Apple phone, iPhone, the cover here on the camera lens is actually a single crystal sapphire. It's optically transparent. It's a ceramic. It's really hard and scratch resistant. But not everything is not every material is crystalline. Not everything. So some things are disorganized. I should actually write this in, and I'm going to define a new term here. Some materials are amorphous. Okay, and what does amorphous mean? Well, amorphous means not organized or not crystalline. Okay, and an example of that would be window glass. And that's a classic example. Got these molecules, and it's a very disorganized structure in there. That being said, there's some order to the molecule, and so oftentimes we'll differentiate between what we call long-range order and, I'll say versus here, short-range order. Okay, versus short-range order. And what does that mean? Well, long-range order has order well beyond nearest neighbor atoms. Okay, I'll show you an example of that in just a moment. And then short-range order means that there's organization only at the level of the first or maybe the second neighbor, nearest neighbor. There we go, neighbor. Whoops. Okay, so let me show you a little bit more what I mean about that. By that, say we were to look at, well, like I did in the last video, I drew this simple two-dimensional lattice to represent a crystal, and I said, well, you know, you could have atoms positioned in these regular positions throughout that lattice, maybe at the corners, like I've indicated here. And so this is an example here, and if this continued, you know, hundreds, thousands of atoms away, the arrangement of atoms continues well beyond just the nearest neighbor. Versus, say, you know, if you had silicon with, you know, 4 oxygens around it or something like that. Well, and then this structure actually could repeat with shared oxygens, and you form this large molecule. this is just a two-dimensional depiction, but you may know that this silicon is going to have what it has next to it, or in a hydrocarbon, you might have a carbon with hydrogen around it, a couple of hydrogens around it, but you only know the order at that nearest neighbor level. Say methane gas. I mean, you've got carbon with 4 hydrogens around it, and you know where the hydrogens are. You in fact know you may know they even have this tetrahedral symmetry. But beyond that, there's no order. So that would only be short-range order versus long-range order, which is what we're really talking about here. Is crystallinity, highly organized materials. So what I'd like to do is show you an example of a highly organized material, and an important one, and that is it's called face-centered cubic. And I'm going to write that in as a new terminology here in the orange color, face-centered cubic, or it's often just abbreviated FCC. So why is that important? Well, many metals have this this arrangement of atoms, and it's also a good structure to become familiar with, because we're going to see that we can use it as a foundation for understanding some ceramic structures, some semiconductor structures, and some of the symmetry that we can learn in face-centered cubic shows up in organic molecules and stuff as well. So it's a really versatile structure to become familiar with. So let's go ahead and draw a cube. And what we're going to do is we're going to use that to understand how these atoms are arranged in a face-centered cubic material, like, for example, aluminum is face-centered cubic. So here's a cube. I'll dash in the back there, those hidden lines, so you can see the full cube. And so it's cubic. What we do is we start off by positioning an atom at each corner. Okay, but I'm going to just pause for a second there. How am I going to depict this? I got to be careful about that. If I were to go back up to this two-dimensional depiction we had here, right, and say zoomed in on just one of these little squares there, and say I wanted to represent this entire arrangement of atoms in 2 dimensions, but only use one little square to do it. Well, what I could do is just take the square, but take a fraction of the circle in 2 dimensions. I would take a quarter at each corner. And so I'm going to do a similar thing with my cube, but now that the cube is in 3 dimensions, the corner positions contain actually 1/8 of a full sphere. Okay, so that's what I'm going to try to draw in carefully. Now I won't always draw it this carefully, but to first introduce the topic, I'm going to try to draw as if it was just the fraction of the atom that it really represents. Okay. Going forward, often I just draw the little dot because it's a heck of a lot faster than what I'm doing right now. But I find when I'm first teaching the topic, a lot of times students really benefit from seeing it depicted a little more carefully like this. And then there's the face-centered positions, so up in the top in the center of the face there, and then on the right side face in the center, on the front side in the center, and then the opposites. So from the top we have down to the bottom. There would be one down here. From the front to the back, there's one in the back of the center of the back face, and then the right, we can go all the way over to the left, and the counterpart over there would be on the left side face in the center position. So each of these corners, as we mentioned, has 1/8 of an atom or of a sphere, and there are 8 corners. So we get 1 atom contributed from the corner positions within the cube only, right? And then there's 1/2 of a sphere on the center position, and there are 6 faces, so we end up with 3 for a total of, in the FCC unit cell, 4 atoms within the cube. So now armed with that, it's actually interesting. What we can do is we can now calculate a property, and what we're going to do is we're going to calculate the density. So the density we addressed in the previous lecture should be the mass per unit volume. So could we calculate the density of, say, aluminum from this, from knowledge that it has the FCC unit cell? Yeah, well, of course you could. And so it would be mass per volume. I'm going to write it down, write it out here so we have a bit of space. Okay, the density is going to be then equal to the number of atoms in the unit cell times how much each atom weighs. And what's that? Well, that's the atomic weight, or molar mass. Okay, and then we're going to divide by the volume of the unit cell. Now, to get the volume of the unit cell, I should specify that we define the edge length here of the cube as A. We call that the lattice parameter. Okay, lattice parameter. And this is the volume of the unit cell. Now, I just want to stop for a second here and look at the units that we've got so far. So we've got units of number, atomic weight, or molar mass from the periodic table has units of grams per mole. And then in the denominator there we have the volume of the unit cell, which will have length units cubed. So we look at this and we say, well, this is irritating. We're trying to get units for density of mass per volume, but we're not getting there. So what are you missing? Well, what has units of number per mole? Well, of course, Avogadro's number. So if we add Avogadro's number into the denominator, and then we get number per mole, the units work out. And this is our final equation. We've got density units, grams per cubic meter in this case, which you could convert later to something like grams per cubic centimeter. And so this is going to get a little red box because it's an important equation. And I will just complete this by identifying that that's the Greek letter rho. That is the volume of the unit cell. Just give myself a little bit more room here. The volume of the unit cell. This is, of course, the number of atoms in the unit cell. And that's Avogadro's number. So there you go. From just our knowledge of the crystal structure, we can now calculate a property like the theoretical density. Thank you.